Yeah. So today I'm going to discuss three major concepts. So three problems I'll try to cover. Yeah. Yeah. So today I'm going to cover three problems. I'll try to cover three problems. In the first problem, I'll discuss the concepts regarding carryover moment, distribution factor, etc. In the second problem, we'll discuss about shear center a little bit. And in the third problem is related to structural dynamics. So these concepts I'm going to cover today. In the first problem, and of course, after every problem, I'll ask you to solve the practice problem as well. It will be similar to the problem I'm telling right now. Okay, so the first problem is question number 51 of set 1 gate 2022. Consider the linearly elastic plane frame shown in the figure. The members HF, FK, and FG are welded together at joint F. The joints K, G, and H are fixed supports. K, G, and H are fixed supports. A counterclockwise moment M is applied, counterclockwise or anti-clockwise we can say, moment is applied at joint F. So there is a moment also at joint F. Consider the flexural rigidity EI as this is 10 to the power 5 kilonewton meter square for each member and neglect the axial deformations. So the question is, if the magnitude of the support moment at H is 10 kilonewton meter, it is given that the moment at H, the magnitude is, we are not given the directions. So let's assume it as this. So the value of this moment is given as 10 kilonewton meter. We are asked if the moment at H is 10 kilonewton meter, what will be the applied moment? Okay, so we need to find the value of this applied moment M if the moment at H is given. Okay, so only one moment is given, that is the moment at H, and we need to find the value of the applied moment, right? I hope the question is understood. To solve this problem, the concept related to a stiffness method of structural analysis, you can refer to structural analysis 2 lectures by Professor P. Banerjee of Department of Civil Engineering, IIT Bombay. Okay, so before going into the solution, I'll discuss few important concepts which will help in solving this problem. I hope the problem is understood. I'll tell you again. In this problem, there's a frame, right? It's a frame carrying member FH, FG, and FK. There is applied moment M as shown here. The value of this applied moment we need to find out. The given thing is the moment at H is given to us, which is 10 kilonewton meter. The moment at H is given and we need to find the value of applied moment. Okay, so for this type of problem, we need to have to know some concepts. Like the first concept is the concept of carryover moment. Okay, so what are carryover moment? What is carryover moment? Carryover moment is, suppose this is a propped cantilever beam AB. On the hinged side, if we apply a moment M, at A, if we apply a moment M, if we apply a moment at A, there will be some moment induced at B also, right? Because if we apply a moment at the end A, the moment B will also be affected, right? So the moment at B, we don't know. Okay, so let's assume the value of this moment at B be M dash. Okay, so this M dash is the carryover moment. So if we apply moment at first joint and the other joint is fixed, so the moment carried over to other joint is known as carryover moment, right? Okay, so this moment is carried over to B point also, hence it is called as the carryover moment. Now what is the value of this carryover moment? If we apply a moment M at A, what is the value of the moment that is carried over to B? Please note that this concept of carryover moment will be used in this problem. Okay, so for finding out the value of this carryover moment, we will use the slope deflection equations, right? So what is the slope deflection equation? MA is equals to mf ab, I hope you know the slope deflection equations, plus 4ei theta a by L plus 2ei theta b by L minus 3ei delta over L. So this is the slope deflection equation. If you want to write the slope deflection equation for end B, moment at B, so moment at B will be, please note, it will be similar to the above, MFBA plus 4EI. Now, if we are calculating the MB, then theta 4EI will be with theta B by L, otherwise the equation will be same, plus 2EI theta A by L minus 3EI delta over L, right? Delta is in case when the support is sinking. So this is not a support sinking case. We'll simplify this equation. So I hope you know the slope deflection equation for calculating moment at A and moment at B. These equations are very similar. The only difference is if we are calculating the moment at A, we are using theta A with 4EI by L, and we are using theta B with 2EI by L, and opposite in case of MB, right? So these are the slope deflection equations. I hope that you know all this, at least the slope deflection equation. Now using this slope deflection equation, I am calculating the value of moment at A. Okay. This concept of carry over moment, I'm just explaining. If you already know the concept of carry over moment, you do not need to do all these steps. You can directly solve the problem. Okay, I'm just explaining this concept. Okay, so what is the value of MA now? MFAB is the fixed end moment. Since this AB beam do not carry any loading, so fixed end moment will be 0. Fixed end moment will only happen if this beam AB will have some external loading. Okay, so MFAB is 0. Will there be any theta A? If we apply a moment at A, will there be any theta A? Yes, theta A will be there because the beam will deflect something like this, right? Will there be any theta B? Can anyone answer? Will there be any theta B? In the comment maybe. Will there be any theta B? Just a guess maybe.
No, ma'am.
Right. There will not be any theta B. Why? Because the end B will be is fixed, right? So this is 0. There is no sinking of support. So this thing will also be 0. Right. So MA will simply be equal to 4EI theta A by L. Right. Similarly, we can calculate MB. MB is MFBA plus 4EI theta B by L plus 2EI theta A by L minus 3EI delta over L. In this case, MFBA is 0 because there are no external loading. Theta B is 0, we know that, right? And delta is also 0 because there is no sinking of support here. So MB will be is equal to 2EI theta A over L. Now we know the value of MA, right? And we know the value of MB, right? Now MA is, we can see that MA is twice of MB because MA is 4EI theta A by L and MB is 2EI theta A by L. So MA is twice of MB. Okay, and value of MB we can write as half of MA. So this is the value of the carryover moment. If we know the value of MA is M here, right? We have applied a moment M. So the value of this M dash is equal to half of M. So whenever we apply a moment at any joint as M, and the far end is fixed, so the carryover moment is m dash, and the value of the m dash will be half of m. So this is very important. It will be used in many problems. The value of carryover moment when the far end is fixed is equal to m by 2, right? The half of that particular moment. So this concept will be used in this problem. So the value of carryover moment will be half of the applied moment in case the far end is fixed. Now, the another concept which we will use in this problem is the concept of bending stiffness. Bending stiffness is nothing but m by theta. Suppose the same beam we take and we apply a moment m, right? So we have already found out the value of MA as 4 EI theta A by L, right? So this value M is equal to MA, or you can say 4 EI theta A by L. So the bending stiffness is nothing but MA by theta A, and the value of bending stiffness is 4 EI by L. Bending stiffness is nothing but m by theta, and in this case the value of m by theta is 4 EI by L. So in case of a in case when the far end is fixed, the value of bending stiffness of that member is 4 EI by L. Okay, so I'll give in after this problem, I'll give you some a practice problem in which the far end may be hinged. Okay, so the value of carryover moment we know. When we apply a moment m, the carryover moment is half of the applied moment. This is the first concept. The second concept is the value of bending stiffness when the far end is fixed is 4 EI by L. The third important concept is the concept of distribution factor. I think two concepts are clear, right? Two concepts is carryover moment concept and bending stiffness concept. Please remember these two things. Now, distribution factor. This is the last thing which we will use in this problem. Distribution factor is, suppose there is a joint, let's call it as O joint. It has a lot of connected members. We'll name them A, B, C, D. And if we apply a moment M at joint O, okay, so the moment M is applied to the entire joint. Okay, so there's and different members are connected to this joint O. So the value of moment shared by each member will be in proportion to the stiffness of that member. Okay, I'll repeat again. The value of moment shared by each member will be in proportion to the stiffness of that particular member. How will this concept be useful to you? We will calculate the stiffness of all the members. So we already know, right? The bending stiffness formula we already know. When the far end is fixed, the value of bending stiffness is 4 EI by L, right? So we can calculate the bending stiffness of each of the members, because for every member, like for member OA, the far end is A and it is fixed, right? For OB, for OC and for OD also, the far end is fixed. So the bending stiffness formula we already know. For example, the bending stiffness of member OA will be equal to 4 EI, suppose EI is constant for all the members, suppose, by length of member OA. Similarly, KOB will be equal to 4 EI by length of OB. Similarly, for OC also, because in OC also the far end is fixed, right? So 4 EI by LOC, and finally for OD also the bending stiffness will be 4 EI by LOD. So we have calculated the stiffness of all the members. Now what is distribution factor then? Distribution factor is the ratio of stiffness of the member of that particular member divided by the stiffness of all the members connected to that particular joint. Let's see how we can calculate the value of distribution factor. So distribution factor of, suppose, member OA, we need to calculate. The distribution factor of member OA will be the stiffness of member OA divided by sum of all the stiffness of members which are connected to that joint O, right? So distribution factor for joint OA will be, we can write it as KOA divided by KOA plus KOB plus KOC plus KOD. Right? We know all the values of K, OA, OB, OC and OD, and we can calculate the value of distribution factor. Okay, and in this distribution factor, what do they mean? Suppose the distribution factor by this calculation comes out to be 1 by 4, let's say. Okay, so distribution factor of member OA comes out to be 1 by 4. This means that the moment in member OA will be equal to 1 by 4 of the applied moment, right? So this is the concept of distribution factor. Okay, so in the proportion of the stiffness, the applied moment will be shared to each of the members. And how do we calculate the value of distribution factor? We will calculate the stiffness of all the members connected to that joint, and the distribution factor of a particular member we can calculate by this formula. Okay, so now we'll solve this problem and you'll get to know more about this concept in detail, right? So we know the value of carryover moment. Now we know the value of stiffness of a particular member, and we know what is distribution factor. Any confusion till now? If there any confusion, you can maybe write in the comment. If it's okay, I'll move. Okay, I hope it is fine. So I'll move towards the solution of this problem now. Okay, so in this problem, the same concept is will use the concept of distribution factor. So the value of the applied moment is not given. So the value of applied moment we need to find out, and the only thing which is given to us is the moment at h, and the value of moment at h is given as 10. And using this value of moment at h, we need to find the value of applied moment m, and this is our problem. Okay, so now let's fill this table. Let's calculate the distribution factor. Okay, the overall I'll tell you how we'll solve it. So we know the value of the total applied moment m. In the proportion of the distribution factor, the moment will be shared with the member fh, right? So we can say that member fh will be equal to distribution factor of member fh multiplied by m, right? We have told you this also. So in the proportion of the distribution factor, the moment will be shared. So the moment fh will be equal to distribution factor of fh multiplied by the applied moment m. Distribution factor of fh we will calculate now. Also we know that, right, let's consider this fh joint, right? If we know the value of moment at fh, okay, so the moment at fh will be twice of mh, right? Because this is mh is the carryover moment for this moment at fh. Suppose the moment at fh is mfh, so mh will be half of this mfh, right? So from the concept of carryover moment, so half of this moment will be carried over to point number h. So these few equations we'll use, I'll explain them again, but before that let's calculate the value of the distribution factor first. Okay, so I'm not going to confuse you. Let's calculate the value of distribution factor first and then see how we'll solve. Okay, now for member fh, what is the value of member stiffness? For member FH, the far end is fixed or hinged. For member FH, the far end is fixed. So the member stiffness will be 4EI by L. And what is the length of member FH? Length of member FH is 5. Right? Now, for member FK, for the member FK, the far end is again fixed. So the value of member stiffness will be 4EI by L. What is the length of member FK? The length of member FK will be, this length is equals to under root of 3 square plus 4 square. The length will be 5 meter. Okay, since this is 3 and this is 4, so the length will also be equal to 5 meter for member FK as well. It is equal to 4 EI by 5. And similarly for member FG also, the value of member stiffness will be 4 EI by L, and the value of L is 5 in this case also. So the entire stiffness will be the sum of 1, 2 and 3. Okay, the joint stiffness will be the sum of all the member stiffness. So joint stiffness will be equal to 12 EI by 5. Okay, so the value of distribution factor will be, the value of distribution factor for member FH will be the stiffness of member FH, the stiffness of member FH divided by the stiffness of the entire joint stiffness. So 4 EI by 5 divided by 12 EI by 5 equal to 1 by 3. Okay. Similarly, the joint stiffness for member FK will be the stiffness of member FK divided by the entire joint stiffness. So 4 EI by 5 divided by 12 EI by 5, and the value will be equal to 1 by 3 as well. Similarly, for member FG also, the value of the distribution factor will be 1 by 3. So this means that the entire moment, the applied moment M will be divided into all the three members equally. Suppose the applied moment is 10, so the moment at each of the member will be 10 by 3, 10 by 3 and 10 by 3. Okay. So distribution factor tells us that how the member will be distributed in all the members which are connected to a particular joint. Okay, so we know the value of distribution factor now. Now we know the value of distribution factor. So the value of MFH will be equal to the moment carried by member FH will be equal to 1 by 3 of moment of entire moment. Can anyone tell me the value of MFG? What is the value of MFG? Maybe in the comment someone.
Member 3.
Great. Right. So all the members will carry the same force. So MFG will be equal to 1 by 3 of M. So I hope this is clear to you. Now we know the value of MH. We know the value of MH. The value of MH is given, which is 10 kilonewton meter. And we want to know the value of this value M. Now from the concept of carryover moment, the moment at H will be equal to half of MFH, right? Because the moment applied at F will be carried over to H, and it will be half of MFH from the concept of carryover moment. So we know this concept already. Therefore, since MHF is half of MFH, so we'll write this MHF equal to half of MFH, and the value of MFH is 1 by 3 of M, equal to 1 by 3 of M. So MHF will be equal to 1 by 6 of M. The value of MHF is already given to us, and the value of MHF is given as 10, equal to 1 by 6 of M. So the value of applied moment M will come out to be 60 kilonewton meter. So we finally get the value of M, the applied moment M, as 60 kilonewton meter, and this is our answer. So this was a fill in the blanks type of question. We need to know the value of M, applied moment M, in kilonewton meter. So the answer will be 60 here. Okay, so it was a 2-mark question. So if you already knew the concept of distribution factor and carryover moment, you could easily solve this problem in a minute. Okay, it was a very simple problem, and yet it was a 2-mark question. So now, if is there any problem with this? Otherwise, I'll give you a similar practice problem now. Any confusion? You know the value of carryover moment now, distribution factor, and yeah, and now then we have solved the problem. Now I'll give you a practice problem similar to this. The first question is, what is the value if there's a simply supported beam, okay, and we have applied a moment M at A. So what is the moment at B? MB. What is the value of MB? Anyone? If we have applied moment, it is a very simple question. If we have applied moment M at A, what is the value of moment at B? Should not take that much time. In the comment, maybe someone want to try? Ma'am, 0. Yeah. I hope everybody would know this because B is a hinge support. At least you should respond. I don't know what state, what level you are. So please um, try to interact. Okay. Otherwise, I won't know कि कितना समझ आ रहा है. Please let me know. Okay. Okay. So moment at B will be 0. Why it will be 0? Because it does not depend upon the value of moment we apply at A. B is a hinge support, so A will always be 0. Now the second question is, find the stiffness of member AB. Earlier we have solved the problem in which the far end was fixed. In this case, the far end is hinged. So I want to know the value of member stiffness when the far end is hinged. The value of stiffness of member I've already told you will be m by theta. So if anyone could calculate the value of ma by theta. Do you want to try? Anyone? So I'll give you 2 minutes and then I'll solve. Please do it on your own. Even if you do it wrong, it doesn't matter because you will remember it better if you have tried it already. Okay, so please try to calculate the value of ma by theta. If anyone has already done it, so he or she might tell me. You have to use the same slope deflection equation again. Okay, so I'll solve it for you. Let's see if you have done it right or wrong. So ma by theta will be simple. So ma will be equal to, from the slope deflection equation, it will be mf ab plus 4ei theta a by L plus 2ei theta b by L, right? Minus 3ei delta over L. Since there is no case of sinking of support, so this will be 0 and this will be 0. Theta A and theta B will not be 0 in this case because both ends are hinged. If the end is fixed, then only theta A or theta B will be 0. So MA will be equal to 4EI theta A by L plus 2EI theta B by L. Okay, now I'll just remove it. So similarly, MB will be equal to MFBA plus 4EI theta B by L plus 2EI theta A by L minus 3EI delta over L, let's say. So there's no sinking of support, so let's remove it. MB will be equal to, MFBA is also 0, so it will be equal to 4EI theta B by L plus 2EI theta A by L, right? Now MB is 0, we already know, right? Because B is a hinge support, so MB is 0. This means that 4 theta B is equal to minus of 2 theta A, or we can write it as, no space now, let's remove it, or we can write it as theta A will be equal to times of theta B. Okay, right? We will put this value of theta A or theta B in this problem. At least do it, try to do it now. Put the value of theta A in this. Okay, let me do it. MA will be equal to 4 EI theta A by L plus 2 EI by L. Theta B is equal to minus 1 by 2 of theta A. So finally our answer will be MA will be equal to 3 EI theta A by L, right? So MA by theta A is equal to 3 EI by L. Okay, so earlier when the far end was fixed, the value of stiffness was 4 EI by L. Now we know that if the far end is hinged, the value of this stiffness will be 3 EI by L. So please remember this. Maybe then in the next year they will give you a problem in which instead of the far end being fixed, one of the end may be hinged. So in that case, to calculate the value of member stiffness, instead of using 4 EI by L, you have to use 3 EI by L. This is the only thing you have to keep in mind for these type of problems. Either you have to use 3 EI by L or either you have to use 4 EI by L. Luckily in this problem, every member was fixed, so you don't have to think about it. You just put it 4 EI by L. If one of the member would be hinged, far end would be hinged, so in that case you have to use 3 EI by L. Okay, so these two things you have to keep in mind. If the far end is hinged, you have to use 3 EI by L instead of 4 EI by L. So this is the problem now. Please try to solve it and tell me the value of MA, moment at A. This is a similar related problem like we have discussed. So the value of applied moment is given to us and we need to find the value of MA. In the earlier problem, the applied moment was not given, and in this problem, applied moment is given, but we need to find the value of MA. At least tell me the value of member stiffness. Okay, let's see that we have to analyze the joint B in this case. So the members connected to it is BC and BA. Please quickly tell me the value of member stiffness or the stiffness of member BC. What will be the stiffness of member BC? In term,
And 3 EI by L, that is equals to EI by L. Sorry, EI.
great. So for this time, let's call it as in terms of EI by L. So 3 EI by L, let's call it. Okay, so maybe about rabbit. So 3 EI by L, and here the value of L is 3, right? And what will be the value of member stiffness of member BA? Member stiffness BA will be equal to 4 EI by L. Why 4? Yeah. Why 4? Because the far end is fixed. So in this type of problem, you just only need to consider whether far end is fixed or hinged. So the sum of the sum of this stiffness will be equal to 2 EI, right? The distribution factor will be 1 by 2 and 1 by 2, right? The distribution factor will be equal to 1 by 2 and 1 by 2. Can you now tell me the value of MA? Anybody in the comment? You have done it correctly till now. You've told me everything correct. So we have found out the value of distribution factor. So can you tell me the value of at least MBA? MBA will be maybe in the comment someone.
2010.
MBA will be
10 kilonewton.
Very good. MBA will be 10 kilonewton. And what will be the value of MAB then?
In 5.
Very good. Very good. So great. So MBA will be equal to from the distribution factor, MBA will be equal to half of applied moment. So half applied moment is 20. So MBA is equal to 10 kilonewton meter. 10 kilonewton meter, and from the concept of carry moment over moment, MA will be half of MBA because half of the moment will be carried over to the far end. So MA will be half of MBA, and MBA was 10, so MA will be 5 kilonewton meter. Okay, so this type of problem you may get next year. Maybe they may add a number of other joints as well. Okay, but the only concept for this type of problem is the concept of carryover moment and the distribution factor. And the thing which you keep want to, because in maybe in a hurry you would forget whether to use 3 ei by l or 4 ei by l. So this thing you should keep in mind. For if the far end is hinged, you have to use 3 ei by l, and if the far end is fixed, you have to use 4 ei by l. Other than this, there's nothing much in this type of problems. Okay, so it is clear, I hope. So I'll quickly move towards the another question. The another question is related to the concept of shear center. Okay, so the question is question number 16 of set 1 gate 2022. So consider this the cross section of a beam made up of thin uniform elements having thickness t, where t is very less than a. As shown in the figure, the coordinates x, y of the points along the center line of the cross section are given. So the coordinates are given for different points. For example, for point H, the coordinate is this. For K, the coordinate is this, and for J, the coordinate is given to us. Now, we are asked the coordinates of shear center of this cross section. So we need to find the shear center and tell the coordinates of the shear center for this cross section. So it was a 1 mark question, and it's a very easy problem. Just you need to know what is shear center and some facts related to shear center. Okay, let me tell you what is shear center. So shear center is a point in a cross section through which if the load passes, then the member is subjected to pure bending and no twisting. Please keep that in mind. Shear center is a point through which if the load passes, there will be no twisting. This is a very important thing. There will be pure bending and no twisting. So no twisting at shear center. Please remember this point. So some of the important points related to shear center are: shear center always lies on the axis of symmetry if exist. Suppose there's a T section. Okay, so in this T section, there is axis of symmetry, right? This is the axis of symmetry. This is the only axis of symmetry that exists. So the point is shear center always lies on the axis of symmetry. So the shear center for this cross section will lie anywhere in this axis of symmetry. It will not lie beyond the axis of symmetry. Okay. The second important concept is if the two axes of symmetry exist, then shear center will lie on the point of intersection of the two axes. For example, in a rectangular section, let's say there's a rectangular section. So in this section, two axes of symmetry exist, right? This vertical axis of symmetry is also there, and horizontal axis of symmetry is also there. So it is said that if the two axes of symmetry exist for a particular cross section, then shear center will lie at the point of intersection of these two axes. So this will be the shear center for this cross section. So this is another important thing. The third thing is shear center can lie outside the cross sectional area. So in the two things which I have cross sections which I have discussed till now, the shear center was inside the cross sectional area. But in some cases, shear center can also lie outside the cross sectional area. Suppose for this member, there is only one axis of symmetry, right? So shear center can lie outside the, so shear center will lie on the axis of symmetry that we know, but shear center can lie outside the cross sectional area. So shear center for this member can lie outside the cross sectional area also. The fourth important point is shear center of the section consisting of two intersecting. This is very important, very important. The shear center of the section consisting of two intersecting narrow rectangles always lie at the intersection of the center lines of the two rectangles. I will tell you what is written. So suppose there are two narrow rectangles. Okay, suppose there are two narrow rectangular things and they are intersecting at a point. So shear center will lie at the intersection of their center lines. The shear center will lie here at the intersecting point. I'll discuss it some more. So basically these 4 points and the definition of shear center you should remember. So maybe In some time they can ask you, they can give you four options, and in one of the options they can write shear center cannot lie outside the cross sectional area, and they might ask which of the following statement is false. Okay, so you have to keep in mind that shear center can lie outside the cross sectional area as well. So they can twist and turn these 4 points and give you a problem related to this thing. So now the concept which is related to our problem, that is the intersection of narrow rectangles, because in our problem also we have two rectangular narrow sections which are intersecting. So this section and this section, and they are intersecting at a point. So this fourth point is important for us. Shear center of a section consisting of two intersecting narrow rectangles always lie at the intersection of the center lines of the two rectangles. For example, so we'll use this concept. For example, here in this case there are two intersecting narrow rectangular section, so shear center will lie at the intersection point. In this case also the shear center will lie at the intersection point. So it's very simple. Okay, we have to just see the intersecting points and shear center will lie at that point. Now in our problem, I hope it is clear now. So shear center will lie at the intersecting points, but we are asked the coordinates of the shear center. So coordinates we can easily see. So this coordinate of this particular point. Okay, so this is x-axis. So the coordinate of this point is 0. So the coordinate of here, the coordinate will be x will be 0 and y will be 3a. Y will be 3a. So 0 comma 3a will be the coordinate of this particular point, right? X is at 0. X is at 0. So it is on the x-axis only. And how much deflected from y? 3a. So the coordinates of this point of shear center is 0 comma 3a. So our answer will be 0 comma 3. I think it is very simple, right? This was y-axis and this is x-axis. So coordinate will is 0 comma 3a. So our answer will be a. Okay, so it was a 1 mark question and it is very easy. If you know this important point, that shear center of two intersecting narrow rectangles will lie at the point of intersection, then you could easily tick mark this, find this option. I hope it is clear to you, and if it is clear to you, let me ask you one related problem. Okay, is it clear? Right, I think it was not very difficult. So these 4 points and the definition of shear center, please remember that. Okay, so now the problem. Huh. Please identify the wrong diagram in this. There are four diagrams which are given to you: A, B, C, D. S denotes the shear center and G denotes the center of gravity. Okay, of the cross section. Please identify the wrong diagram from these four options. CG is given to you, and okay, that's great. That's great. I hope now I think the point is clear to you. The value of the shear center will be the diagram D is wrong. Why D is wrong? Because it's a case of two narrow rectangle intersecting, and the shear center should lie at point G only, not at here. Okay, so this is a wrong option. So this kind of problem related to this concept can be given to you. Okay. Now, two problems we have already discussed. Let's discuss one more problem. I hope till now there's no issue. Okay, now we'll move towards a slightly different domain of structural dynamics. So I've in this, I think second or third class, I've already told you a problem similar to this problem. So I've already told you that structural dynamics, although it's a vast subject, but in GATE they don't generally ask very tough questions from structural dynamics. So few important formulas of structural dynamics, if you'll remember, you'll able to solve the problem of structural dynamics. Okay, so the first formula I told you already, that the value of natural frequency, what is the formula? Omega is equals to under root of k by m. and the value of time period is 2 pi by omega. These formulas at least you should remember, because most of the question they usually ask the value of the frequency and time period. Okay, so these formulas you should keep in mind, and it's a 2 mark question and it's a very easy problem. If you'll remember these two formulas, then you'll get this problem within a half a minute. Okay, so omega equal to under root of k by m, this you should remember. And T, if you are even leaving in the entire structural dynamics, don't please remember at least these two formulas, right? So the problem was an undamped spring mass system with mass m and spring stiffness k is shown in the figure. The natural frequency and natural period of the system are omega and t respectively. If the stiffness of the spring is doubled, okay, so stiffness of the spring, let's say this the stiffness is given as k, so the stiffness of the spring is doubled and the mass is halved. Okay, so there was a system, now they have modified a system, they have a modified system now similar to this only, but in now the mass is halved. So this is suppose m dash and this is k dash, so mass is halved, m dash is half of m and stiffness is doubled, k dash is equals to twice of k. So this is the modified system. So we are asked, if the stiffness of the spring is doubled and the mass is halved, then the natural frequency and natural time period of the modified system are. So this is the modified system and this is the given system. Okay, so I want you to try. I've already told you the concept, sorry, the formula. So omega is under root k by m. I'm writing it. Omega is equal to, it's a very simple problem. Omega equal to under root of k by m and t is equals to 2 pi by omega. So this is the two formulas you need to use. So you just need to find the value of natural frequency and time period for this modified system. Please try it. I'll give you a minute maybe. Please try to solve this problem.
Option D.
Option D. You this is, it will not change according to you, right? But why? Omega dash you need to find out and t dash you need to find out. Please try it again. Omega dash and t dash. Any other?
Ma'am, B, ma'am.
B. Okay.
Yes.
Any other? So B, you are saying that omega dash is omega by 2 and time period is double, right? Okay.
Yes, ma'am.
Let's see. Now natural frequency is k by m and time period is 2 pi by omega, you already know. Now in the modified system it is given to us that k dash is twice of k and m dash is m by 2. Okay, so let's put the value here. It's twice of k and k dash is twice of k, right? And m dash is m by 2, m by 2. Hmm? So it will be equal to omega dash equal to under root of 4k by m, or we can say that omega dash is equals to 4 will come out. It will be twice of under root of k by m, and omega dash is equals to twice of what is under root k by m? Omega, right? So omega dash is twice of omega. So first thing is omega dash is twice of omega, right? So we can easily find that first option is right even from without solving t dash. Okay, I hope it you're like okay with this. Now what is the value of t dash? T dash will be equal to 2 pi by omega dash, and omega dash is twice of omega, twice of omega. Okay, and we can also write that t dash is equals to 1 by 2 of 2 pi by omega. So t dash will be equal to t by 2. I hope it is clear to you. So t dash is coming out to be t by 2 and omega dash is coming out to be twice of omega. So what is the correct answer? Option is option number A. Right? Any confusion in this? I hope there should not be any confusion. Right? So option A is correct. Is there any confusion? Should I explain it again or it's okay? You're yes or no? Fine.
No confusion, ma'am.
No confusion, right? Okay. Okay. So this was a very simple problem. You just need to apply that concept. So maybe for today I've planned these three problems only. Let's give you a homework problem. Please try this problem at home. Okay, so length of all the members is L only, and we have you have applied a moment M. M, the value of M is 100 kilonewton. EI is constant. You need to find the value of MAB and MAO. MAO and MBO. Okay, so this was a similar problem related to the first problem we discussed. Any confusion till now? So today we discussed three important problems. First one is related to structure analysis 2, and second one is shear center, and third one is related to structural dynamics. If it is clear, then I'll close the session for today. Please try this problem at home. Maybe in the next session, I'll discuss some different problems. I hope 2022 problems I've already covered. Now we'll shift to maybe a problem related to 2011, even of 2011. So let me ask you a question. Maybe if I have that. I don't think so. I have that. Let's ask. Okay. It was a 2000. It's a 2011 problem. Okay. So you should try it at home. This one also, it's a very interesting problem. This is L by 2. This is also L by 2. Okay, so this is the thing. And let me ask you, if for the first structure, it's a like a homework problem for you. Let's see for structure B, what will be the moment at the midspan or maybe at O? What is the moment at O? Please note these few questions I wanted to ask. Is there any difference between structure A and structure B? If yes, what is that difference? And find the value of, because they are looking like very similar, just the part O is like slightly up in case A, and in case B it is like in a straight line. Is there any difference between structure A and structure B? If yes, then what is the difference? And please find out the moment at point O for both case A and case B. You'll be surprised to know the result. I'll tell you this solution in the next class maybe, but it's a very interesting problem and it's a GATE 2011 problem. Find the moment, the problem was to find the moment at point O, okay, for case A. So please try this problem at home, and in the next class I'll discuss this thing. I hope I'm clear for today. If there is no problem, then I'll close the session for today. Thank you for listening. It's okay, right? Shall I close now? I hope there's no problem. I'm closing the session now. Thank you very much for listening, and please try these two problems at home. In the next class, I'll discuss this problem. Thank you.
Thank you, ma'am.